Um, Thank you so much for the flexibility. Now I will give you a survey in our activities, but also my main focus is, since we have seen already in the last presentation outstanding concepts on, let's say, a lab scale, our role, I think, always in international collaboration is that we are doing as well the machine manufacturing. So although we are active in creating devices and structures, but we also always thinking, how can a production system be developed, which allows a larger scale, million pieces per year or whatever. So first of all, you mentioned my name is Thomas Gries, right? I'm from Aachen University, the Institute for Textile Technology, and it's called, now we call it International Center for Sustainable Textiles. Why? Because in all our means, we try to be utmost material efficient. We try to invent fiber architectures which uses fiber materials at a minimum amount of materials, sorry. And of course, we also combine it with digital process control. And then, of course, Aachen University. Where in the hell is Aachen? Of course, you know Europe. This is Europe. Well, it's Europe also including Great Britain. So anyway, it's Europe. The question is, where in the hell is Aachen? You probably know where Rome is or Paris. Let's take a closer look. There is a border between Belgium, Netherlands, and Germany. And if we zoom in, then right in the middle between the international airports of Düsseldorf, Frankfurt, Brussels, Paris, just 1 hour journey apart, it's in the middle is Aachen. So for all of you, please feel invited to stay in Aachen, coming as a visiting researchers, as a visiting lecturer, joining our efforts, and it's easy to reach. Although you probably don't know where Aachen is, but it's just 1 hour drive from the most important international airports in Europe. Now the Institute, we cover actually today, my talk is about 4D Textiles, but our institute covers any kind of fiber manufacturing, melt spinning, solvent spinning, electrospinning. We do the yarn technology, the fabric technology. Of course, the fabrics we use can also be produced at our site. We design composites, so combinations of material, and typically we end, especially in the field of technical textiles, with semi-finished part. So all these parts, also those who will be present later, are today a part of a bigger system. So in many of the international collaborations, we do the system integration. For example, if you have a nice device, an actor, a sensor, whatever, but the question how to integrate in something larger one, this in many international collaboration, our task is not only to develop a material, a textile material, or the production technology, but to integrate it in a solution which can then serve applications in all needs of modern life, mobility, building, health, environmental, and ICT. So this is just an overview. Basically, we are located in the Faculty of Mechanical Engineering. So we develop processes, we develop fiber-based materials and textile structures. But many cases we do also the mechanical engineering of the equipment. Many materials start with polymers, but we also process ceramic fibers, carbon fibers, glass fibers. We can make carbon fibers and glass fibers, one of the very few chairs worldwide. And of course, we develop the 3D structures, the textiles for fiber-based composites. We are working much in technical textiles. We also deal with the joining of textiles, which is necessary for the system integration. And in that field, especially in this division of my institute, we have the group dedicated to 4D textiles, because actually 4D textiles is also a fusion between different kind of materials, textiles, so fiber-based materials, and non-textile materials. And of course, with all this, we do simulation and measuring. A lot of measuring technology, which is used for new textile materials, has been developed at our institute. Just to say, seems to be a big scope. Yes, it is. But we have in totally in our institute, under my supervision, 450 people working on all these different topics, but mainly fiber-based materials and the production processes. Okay, now to 4D Textiles. So this was the end of the commercial block, but it's not, I don't want to say it like that. It's also, please take this pre-words, but also what comes now as an invitation to Aachen. So we are pretty aware what we can do, and we are also pretty aware that we cannot do everything. We need collaboration, and so please feel invited to join joint initiatives to bring new materials, especially today. 4D Textiles a step further. Of course, it starts with simple geometries. We use this kind of rectangular, but also round types and others to try different compositions. So different thickness, different pretensions, different also content of for example, elastane, but also the difference in the thickness of the 3D print structure, so that we understand what are the influences on the mechanical behavior. And here, this is of course also one example where we work together with the University of Massachusetts in US, since we are pretty strong in doing the experimental part and also to do the geometrical model. But then Scott Stapleton at the University of Massachusetts, he does all this modeling and simulation of the structure. So it goes hand in hand. So let's say the physical part, the experimental, but also the testing, 3D measurement, metrology is done with us. This modeling and simulation is done at our partner. Then, of course, so this is a basic structure. Then we work on, since we're mechanical engineers, on the design principles. This is only a short part of it to make you understand how we work. So we defined different elements, for example, local stiffening. This, for example, I especially choose this topic because 3D printing on textiles does not necessarily be printing a beam on a membrane, but it can also be printing a tile on a membrane. So we say, is the local stiffening continuous? Is it has it a certain geometry? Is it a full printing? Is it like a tile? Is it a beam printing? This is a kind of modular toolbox. Then, of course, those elements which are printed on the textiles, they are, for example, connected. They either connected just by the textile, we call it textile hinge. And then here you can have, of course, one-dimensional or functional, zero-dimensional, one-dimensional, like a linear hinge, or they can also be 2- or 3-dimensional. And then, of course, what we also decide is we can print the hinge. The print can be a hinge of the same material, but with a different geometry, like you have very much in the design from polymer parts, but it can also be using a different material, for example, elastomer instead of thermoplastic material. And last but not least, also we played around with the adhesions. So, for example, we printed on, attached to the textiles, but we also printed with a small gap. So it's only partially connected to the textile. And this gives you a structure like you most likely have in a kind of umbrella. So you can fold up structures out of the structure. And then you have a more or less textile membrane, but underneath you have a 3-dimensional structure like a framework, for example. Out of that toolbox, then we design together with those who need these kind of morphing materials the right structure. So it's a kind of modular toolbox design, which serves then the design thinking purposes of the creation of the product. We use also different materials. So we have in our institute a set of roughly 20 or 15 plus printers, and many of them, of course, work with the traditional thermoplastic materials like polyamide and PLA, but and equivalent ones. But we also, by the way, it must be said that through our spinning, monofilament spinning activities at our institute, we also can make individual mask-tailored or tailored kind of printing wires, modified by particles which can be heated up and so on. So thermoplast, of course, is a backbone. But then, of course, we recently also went into silicone printing, elastomeric printing. And last but not least, I will show you later that we also designed equipment where you can functionally grade the material either in Z direction or along the printing path. And this is how it looks like. So this is, if you mix it 1-to-1, side by side, then of course, for example, you can improve the interface. So you have the highly elastic textiles, then you print directly on the textile a more, let's say, a high elongation material. And on top, you print the more stiff material. This takes away, of course, shear forces out of the interface and makes the printing on the textile more durable. And of course, it must be said, a lower viscose component A leads to a better penetration into the textile, which gives you a kind of geometrically anchoring. So this is a concept which we developed recently. I will later show you also the machinery for that. So now, after all these different concepts in geometrical structure, in materials, then, of course, the big question is where actually our heart or core is. What does the machine look like? Because you see a lot of 3D printing, some of them with a hexapod structure, some of them is XY actors. And here we are flexible. We have in our group, we have an institute dedicated to automation. They can use open kinematic robots. They can be closed kinematic robots. They can use XY devices and others. One example which we developed with a company together is a roll-to-roll printer. So the first 4D textile roll-to-roll printer with the company Schneider. And we were responsible for developing the basic production principle. We tested the prototype, and later together with the company Schneider, we developed a commercial production, 1 meter width, roll-to-roll, in order to produce continuous wise 4D printed materials. But then, of course, when we started the development, people came to us and said, "Oh, this is nice, but we don't live in a tabletop world. We also have to print, for example, a roofing membrane for a tent or civil engineering. So the dimension of the textile shall be maybe 3 meters width and continuous long." And so we take it a step further, which I'll show later. We also worked on using the typical closed box printer, but for example, printing tubular structures. Tubular structures are very well appreciated if you make, for example, work in the medical field and you want to develop 4D textiles, for example, for fingers, for arms. For doing this, especially we had a project on ambient assisted living for old people to make a gripper as a kind of glove to support the fingers. Then we developed here the special printing bed, which is a rotary move, in order to also to be able to produce fingers in a small value, or to produce sleeves for arms and also for legs. So this was a rotary printing device. And then I mentioned dimensions can be even bigger. Especially if you go to the application in building and architecture. And therefore, we developed this kind of HRV printer, which overcomes the limitation of 3D printing by the chamber size of the 3D printer. And here, by doing so, you almost can print 4D structures with an unlimited extension. If we change the material, for example, if you combine materials, thermoplastic with elastomeric, thermoplastic with silicone, thermoplastic A with thermoplastic B, then of course you have to develop special printer heads where you can switch. So this here is one example, but we also developed others. It's a multi-material printer. In this case, we have two extruder combined, and we either can extrude side by side or top on bottom, but we also can change the content from 0 component A to 100% component B A, and on the other hand, change it from 100% B to 0% B. So this kind of blending across the printing line is also possible with this multi-material printer. The main thing is what we are developing is how can today's structures, because there are 3D structures, textiles or non-textiles, into structures which are integrated, for example, self-ascending, evolving structures, also biomimicking, because if you take a closer look to the nature plays very often, like if you, for example, think of a bat wing, they combine membrane structures, and always typically very elastic membranes like skin together with bones type structures. And this actually is one concept which we also follow with 4D textiles. And then, of course, we also have developed morphing structures for improved aerodynamics or special permeability. These are just one examples, but they only shall show you the variety of topics we cover. But at the end of the day, we always, when we look at a certain kind of application, we always have it in our genes, being mechanical engineers. How shall a production system look like? A production system with quality control, which is able to produce these structures under industrial environment. And this again is just only a handshake towards you. Please, if you want to upscale processes or develop production systems, CE proved or whatever, just give us an email or call. So these are just some, we do the modeling. We have always, in many cases, we use a digital twin of our processes. In many cases, also we couple the design of the model for the design with the control of the process, so having a process model, and with the model of the final product. And then you see here, for example, this was one of the gloves which supports gripping an apple. I think I've talked about that last time, but we're also working in the field of build tech, for example, a roofing membrane which can open and close so that you change the translucency from the membrane. And of course, developing this, we're using integral processes like the Scrum methods and the design thinking, integrating also those who apply those structures. Yeah, so what we're doing now, the material innovation goes further on. So whenever we try a new material, then somebody comes around either from the institute or from outside and can you do this or that? And then again, we think about how can we change the 3D printer in the process. So that's why we also do some 3D printer innovation to play around with the material to overcome the obstacles of the existing systems. The design principle, when we design as such, it's not only that we integrate engineers with a structural mechanical background or material background. We also integrate the applying people, so that the user domain, but also the designers. Simulation, as I said, our institute by heart does much more the, let's say, mechanical modeling, and also do the constitutional laws of the material. But for the real modeling skill, we have our partners. Simple modeling we can do as well, no doubt, but especially these 4D materials, since they are highly deformable, need special FEM, which is not our core competence. Here we work together with capable people worldwide. And the product development, we join here forces also with others. So there are people around for biomimetic design, for design in the certain application domain, because architects for the building, product designers for the product design, and maybe others. Here we work with teams, typically 50 to 60% people from our team, but also very open for others to cooperate. Yeah, and this, of course, I think shall be enough invitation. So I hope I could make you clear how our philosophy is, and also the most important take-home message for you today from my speech is that we are focusing very much on the production system. So whatever idea you have, with fancy devices like we have seen in the previous presentation, combining polymer with ceramics, combining operation is in our genes, and we want to either, if you have ideas, either if you have certain modeling and simulation capabilities. So our main focus remains the production technology and its validation and the scale up. And I think this is an ideal requisite and a precondition for a lot of collaboration. And our team is very much looking forward to join your efforts and achievements with our capabilities. So my final word is, let's bring 4D textiles to the user, because at the end of the day, if it is successful, it has to be a user-centered product. And let's bring all the creative minds and game changers together. Let's cooperate for the future of 4D textiles. Thank you very much.